Columbia University with us. Brian got his PhD at Berkeley with Elliott Quire before taking an Einstein and then a Spitzer Fellowship, both at Princeton. And immediately after that, becoming faculty at Columbia, where he's been ever since. Brian has, in addition, won the Sloan Fellowship while a professor at Columbia. Brian is an expert in a broad variety of areas in high-energy astrophysics and compact objects, stellar physics, and has also been a leading theorist in many of these ideas about multi-messenger physics. We're very lucky to have him today, and he'll be telling us a bit about the really exciting things that have been happening. Thanks, Brian.
Thank you. It is indeed a very, let me put my jacket here, very exciting time. I'm sure since you have some local people that were very heavily involved in this discovery that you have already heard quite a bit about this neutron star merger. And I'm certainly not going to cover all aspects of the phenomenon. I'm going to try to paint very quickly a very broad brush picture about what happened in this event. But I think it's exciting for many different reasons. I mean, we have the first confirmation of this long-held idea that there's a connection between merging neutron stars and gamma ray bursts potentially, and also this long-held idea that these mergers can be the source of some of the heaviest elements in the universe. Roughly half of the elements heavier than iron. The only place you can create them in nature is if you take material and you have a very large flux of neutrons radiating that material. This is called the rapid neutron capture process, or our process. You can see an example of it up here. And it's the only way we know to make the very heaviest elements and roughly half of the elements heavier than iron. And we think we have direct evidence in this merger that there was an R process. It did produce quite a bit of material. And we think, at least in principle, we have enough from this one event to claim that these are a major source, if not the dominant source, of these elements in the universe. I came and talked about this probably 3 or 4 years ago or something, and at that point, a lot of this was, very still theoretical. We didn't have any data, so I'm very happy to be able to actually talk to you about an actual event today. And there's many different areas of astrophysics and physics upon which these types of events cover. We have obviously high-energy astrophysics, the plasma physics of what gives rise to gamma ray bursts, particle acceleration. We have the nuclear physics associated with the R process and the material, and we also have the general relativity that tells us why these neutron stars are coalescing and what gravitational wave signals they produce. So there's obviously, and then also all the observational astronomers who actually discovered this signal. So we have really a wide range of collaborators. I just want to remind you that there's, I think everyone here knows this, what a neutron star is, but just there's a number of properties of neutron stars that we don't know particularly well. One of them is what the maximum mass is of a neutron star. We have a few cases where we have fairly well measured masses that are around 2 solar masses. We have some more speculative cases that may have higher masses. Martin has worked on these. But by and large, we don't really know what the maximum mass is of a non-rotating neutron star, how much mass it can support before it will collapse to a black hole. And we're also still debating what are the radii of neutron stars. Again, this is connected to our ignorance of the equation of state of dense nuclear matter. The maximum mass is pretty tightly connected to what the equation of state is at very high densities, about 5 times nuclear saturation density. But the radii of neutron stars, so different equations of state predict different distributions of the radius versus mass. And even within this, we have uncertainties where, in principle, even sort of 10 kilometer, maybe up to 14 kilometer neutron stars were allowed for, say, a 1.4 solar mass neutron star prior to this event. So one thing I want to connect on a little bit with this event is what the merger is also telling us about the properties of neutron stars. Most people know that sometimes neutron stars are found in binaries, mainly detected as pulsar systems, and these binaries lose angular momentum and energy to gravitational waves, at least for a circular orbit in the weak field approximation. This is the change in the orbital period, which was, of course, well measured for the Hulse-Taylor binary pulsar over 20 or 30 years of observations, basically verifying this prediction. And when we know that these neutron stars exist in our galaxy, we know that they're merging in time scales less than a Hubble time. So this was sort of the guaranteed source that LIGO hoped to detect. For instance, the Hulse-Taylor pulsar will completely coalesce in about 300 million years. And so you can do the rough estimate, in our own galaxy of how frequently these mergers occur, and you come up with a rate of about once every, 10,000 years, maybe 100,000 years, which is fully consistent with the fact that LIGO observed one merger in a few years of observations. But anyways, as you probably also know, since you have a lot of people working on LIGO, what they're really sensitive to detecting is the chirp signal, the gravitational waves produced during the final in-spiral as the two neutron stars coalesce. They produce a signal increasing frequency and amplitude. And what they're sensitive to is basically, I think in this event, maybe Kip can correct me if I'm wrong, but basically, at least for a few minutes prior to the coalescence, they were detecting the signal. But then the actual merger itself, when the neutron stars got close enough to be physically touching, most of that was happening at higher frequencies outside of their band. But by measuring this signal, they're able to obtain some accurate constraints on the properties of the merging neutron star. So as you are aware, last August 17th, LIGO detected the first binary neutron star merger. So this, if you just have the two LIGO detectors in Louisiana and Washington, they're largely, though not completely, determining the sky air position by triangulating the arrival time of the detectors. So that gives you this sort of light green contour on the sky, kind of banana-shaped thing, which is quite large. And we've been dealing with many of these since they've been detecting several black holes before this with these quite large air regions. In this case, one of the differences was that the Virgo detector had just come on in August 1st, and so they actually did not detect the neutron star merger, but that non-detection was constraining and enabled the error region from gravitational waves to be shrunk to this dark green error region, which was about 30 square degrees, which was quite nice in terms of following this up electromagnetically. As you're also probably aware, within about 2 seconds after the merger, Fermi, GBM, the gamma ray burst monitor on Fermi, detected a burst of gamma rays, and its localization region was consistent with that of the LIGO Virgo error region. And then within, basically this thing happened over the Indian Ocean. Most of the follow-up telescopes were in Chile, so they had to wait for the Earth to rotate and become dark in Chile. And when that occurred, there was a discovery first by the SWOPE group and then by several other groups within a few hours, happening about 11 hours after the merger, of a fading optical counterpart inside or right outside this galaxy NGC 4993 at a distance of about 40 megaparsecs. So what LIGO measures quite accurately is a weighted combination of the two neutron stars, the so-called chirp mass. But the individual masses are less well constrained. And I think this is the low spin prior, can be between 1.36 and 1.6 for the first star, and 1.17 and 1.36 for the second one. But the data is consistent with them both being an equal mass binary of two 1.36 solar mass neutron stars. I was actually fairly surprised at how well the total mass of the binary was measured between 2.74 and 2.8 solar masses. And that's going to be very important for what the outcome of the merger is and what we can use to constrain the equation of state of neutron stars. So there's a degeneracy between the gravitational wave brightness and the inclination of the binary. If you're viewing a face-on binary, the gravitational waves are more powerful than if you're viewing it edge-on. So the source will tend to be further away. So based on gravitational waves alone, you're only able to say it was between 26 and 48 megaparsecs. But once the galaxy was identified, that broke to some extent that degeneracy. And you're able to say that this was closer to being a face-on binary. The actual angular momentum of the binary was pointed away from us, but within the plane of the sky, the inclination was less than about, depending on whose analysis you buy into, between about 30 and 40 degrees. So we were viewing this event fairly face-on, but I think it's unlikely we were directly face-on, meaning that we would have expected to see a very bright gamma ray burst. And as you're also aware, there was basically this event triggered the largest electromagnetic follow-up campaign in history, probably for any transient. There were claims that about a third of world astronomers were in some way involved with this. I don't know if that's true. But you have the gravitational waves, gamma rays, X-rays, UV, optical, IR, radio, and then each one of these points represent an observation that was taken, not necessarily detection. And the rough timeline is you have the gravitational wave chirp. 2 seconds later, the gamma ray burst arrived, detected by Fermi, and also integral. There was then, as I mentioned, the optical detection about 11 hours later. It was a bright enough transient 17th magnitude when discovered and then fading quickly that was able to actually get optical spectra of it. During the first few days, there was no, once you knew the optical position, you could search with Chandra or VLA and other dishes to look for very faint X-ray or radio emission, and there was nothing detected for the first few days. But a little over a week later, there was a rising X-ray and radio source, roughly about the same time, non-thermal source, and those sources have been actually brightening continuously since then. It's now a little controversial. It seems like maybe they're starting to flatten off. So what I want to try to do is to go through these quickly, at least, and talk about how we might interpret these different counterparts in terms of a neutron-star merger. But first, I want to talk a little bit about what the outcome of binary neutron-star mergers we might expect and how they depend on two things. One is the total mass of the ingoing binary, and the other is the maximum mass of a neutron star, which, as I said, we don't know very well, but is, at least 2 solar masses or so. So if the 2 neutron stars coalesce, if the total mass of the binary exceeds a critical threshold, which is between 30 and 60% of the maximum mass of a single neutron star, the merger basically promptly collapses into a black hole. There might be a little bit of tidal ejecta, but a very low mass accretion disk, and we don't think this will be very bright electromagnetically. And as I'll mention, we don't think that's what occurred in this event. More frequently, you coalesce and you form a differentially rotating neutron star. So one neutron star is sort of torn apart and orbits the other one in a differentially rotating configuration. And it's that differential rotation that, if it's that differential rotation which supports the object from gravitational collapse, we call that object a hypermassive neutron star. But then over some period of time, through gravitational waves or internal viscosity or some other mechanism, that differential rotation is removed, then the object collapses into a black hole. But because that process of shedding angular momentum also carries mass with it, you tend to form a fairly massive accretion disk around the newly formed black hole in that case. It's even possible, if the initial binary is very low mass or the maximum mass of a neutron star is large, that the merger product, even once its differential rotation is removed, even once it comes into a solid body state, it will still remain stable, and it has to lose additional angular momentum from the solid body state, which takes longer generally. And that object will be called a supramassive neutron star, even potentially an indefinitely stable one, that could survive for minutes, hours, or longer after the merger. I should say that the time scale it takes to remove the angular momentum and collapse if you're a hypermassive neutron star is uncertain. In simulations, it can be short as 10 or 100 milliseconds. But that may be somewhat dependent on the resolution of the simulations and whether we're capturing the proper physics. So I'd say there's some uncertainty in that time scale. But nevertheless, I think there's pretty good evidence that this event went through this channel. And this was actually a priori expected to be the most common outcome of these mergers. You can get some similar outcome if you have the coalescence of a neutron star in a stellar mass black hole. But here the outcome depends sensitively on the mass and spin of the black hole. If the black hole is very massive or slowly spinning, it will just swallow the neutron star whole. There might be some kind of radio burst from the interaction of the magnetosphere or something, but probably we're not going to see much associated with that event. But what can happen if you have a less massive black hole or one that's spinning in the prograde sense with respect to the orbital angular momentum, is that you can tidally disrupt the neutron star outside of the horizon and form an accretion disk around it, very similar to the case of a neutron star merger. So you have two very different systems that can in principle produce sort of qualitatively similar outcomes. But it is important that in a neutron star merger you do go through this hypermassive neutron star phase, which may be imprinted in some of the kilonova emission we observed. So I'm just going to show you a simulation. This is not my own work, but this is by David Radice and collaborators, just showing the final stages of the in-spiral of neutron stars. So you'll see near the end, the 2 neutron stars start to exert strong tidal forces on each other to the point that some material is eventually ejected out of the equatorial plane, like a galaxy merger, sort of out of Lagrange points. Then the 2 neutron stars collide together, and the region between them gets shock heated to a very high temperature, and there's basically a cloud of material which is ejected into the polar region as well. It's like squeezing a tube of toothpaste or something. And then you form this differentially rotating peanut-shaped thing, which is losing a lot of angular momentum through gravitational waves, and then ultimately, in this case, collapses in a fairly short period of time. And you have this remnant disk of material that has so much angular momentum it's not immediately incorporated into the whole. But the point I want to make here is that this is a messy process. It's by the time you actually form a black hole, there may be some enormous cloud of ejecta surrounding the merger. So various groups have studied the formation of these remnant accretion disks. If you go through a hypermassive neutron star phase, the typical mass of the torus will be about 1/10 of a solar mass, give or take. It's typically pretty flush up against the black hole, so pretty small torus initially, but as it accretes, of course, it will viscously expand outwards. It's very hot and dense. So all of the initial nuclei that may have been in the outer layers of the neutron star, for instance, are dissociated into free neutrons and free protons. And these disks are not like your standard photon-cooled disks. Photons are irrelevant in this environment. But neutrinos can cool the disk, especially in the midplane where it gets very hot. So these can be MEV sources of neutrinos, but not ones we are likely to detect, unfortunately. Weak interactions are actually quite rapid in the disk. Urca reactions, electron-positron captures on nuclei. And under the electron degenerate conditions which prevail, they tend to drive the composition to be fairly neutron-rich. Even if it weren't made of a neutron star, these accretion disks would be neutron-rich due to weak interactions. So anyways, you can estimate just using your alpha viscosity, or these disks will produce magnetic turbulence, as I'll show you in a second, which cause this matter to accrete onto the black hole. And the characteristic time scale for that is a fraction of a second. So you're accreting 1/10 of a solar mass in a fraction of a second. It sounds like a pretty promising engine for powering a gamma ray burst if you wanted to make one. And the time scale works out relative to the so-called short duration gamma ray bursts, which indeed last about a second or so. And so these were the main theoretical motivations for associating these with mergers even before this discovery. So anyways, what type of counterpart you expect to get from this is likely to be a sensitive function of your viewing angle with respect to the binary axis. As I just mentioned, you get this transient accretion onto the black hole. Presumably the jet will come out in the same direction as the angular momentum of the binary. But just from observing gamma ray bursts, we know a lot about their properties. We have crude estimates of their opening angle. But the basic idea is it's either feeding off of the spin of the black hole or something else through strong magnetic fields. You accelerate a relativistic jet, goes out to some distance, dissipates its energy through reconnection or shocks or some other mechanism. We were just talking about this earlier with Chris. And produces the prompt gamma ray emission, but it's generally thought that this outflow is highly relativistic if it escapes this environment. And so the gamma ray burst is believed to be relativistically beamed into a fairly narrow solid angle. So only if you happen to be within the opening angle of this jet will you actually observe a gamma ray burst and at least a prompt afterglow, which is produced as the gamma ray burst jet runs into the interstellar medium. You get a shock wave. And that is also relativistically beamed. And you'll see that from t equals 0 if you happen to be within the opening angle of this jet. As you are aware, this event was followed by a gamma ray burst after about 2 seconds. But there were a number of weird properties of the gamma ray burst. Well, not weird, but it was delayed by a few seconds after the merger. Why is this the case? Because, there's a few possibilities for why the gamma ray burst could be delayed from when the merger happens. One is if you think a black hole is needed to make this relativistic jet, maybe you had to wait for the neutron star to collapse to a black hole. That could take a while. Maybe you do collapse to a black hole, but it takes a while to generate the magnetic field. You need to make the jet. Maybe the jet has to break out of this cloud of material before it can produce gamma ray emission, because that happens pretty far out here, typically at least a solar radius or so. Maybe it's a light travel time effect. Maybe there's a direct shot for the gravitational waves, but you have to go out here and make gamma ray emission. And if it's far enough out, that additional travel time takes a bit of time. So there's definitely a lot of people working on this, and I'm not going to provide any unique insight here. But another property of this gamma ray burst was that it was about a factor of 100 times less luminous than any short GRB that had ever been observed before. Than the cosmological ones. Now we have some bias against finding the galaxies of non-cosmological GRBs, because the way we localize the galaxies is by detecting the afterglow. And this would have produced, as we know, it didn't produce a very bright afterglow at early times. But nevertheless, there are various people discussing why this event was so dim. Fundamentally, it's probably related to the fact that if there was a successful jet, we weren't within the opening angle of the jet. And as I mentioned, all we really know is we're within about 30 degrees, 40 degrees. So all we really know is that we were within about 0.6 radians, whereas typically with short GRBs, we infer that the opening angle might be 0.1 or 0.2 radians, although that's highly uncertain. So anyways, it's quite conceivable that this event was just viewed slightly off the jet axis. That isn't an explanation in itself, but as I mentioned, first few days there was no detectable X-ray or radio emission, but after that point it's been rising, and it's been largely consistent with a single synchrotron spectrum extending from as far low frequency as we can measure to as far high frequency as we can measure. It's been brightening, and still now people are debating as it sort of flattened or not. Ultimately, this emission we think is produced as the ejecta in one form or another interacts with the interstellar medium surrounding the merger. The original ideas for this were, okay, well, if we have an off-axis gamma ray burst, initially it's beaming its afterglow emission out of our line of sight, but as that jet sweeps up the interstellar medium, it slows down, and eventually it enters into our causal cone, and that will cause a brightening. This is what a lot of people thought when they first saw this. But then it just kept on brightening. This would have expected to produce something that brightened and then sort of faded, but it kept on brightening. And so what people are now talking about more is that we're somehow seeing like lower Lorentz factor material, for instance, that is not necessarily brightening because it's coming into our causal cone, but just because lower Lorentz factor material takes longer to actually sweep up the interstellar medium and longer for it to sort of reach its effective set-off time. And so as we're seeing it brighten, we're basically seeing the energy in lower and lower gamma material. And there are discussions, arguments about what this means. Did this mean there was a successful jet and the jet had some kind of wings to its structure? Does it mean that there was a cloud and the jet failed to escape the cloud, and we're seeing the aftermath of that failed jet, the cocoon from that failed jet? To me, all we can really say is we're seeing about 10 to the 49 ergs in gamma between 3 and 10 material. Okay, that's all we can really say, because it's really hard to discern from what we see whether there was an off-axis successful GRB. I'm not saying we have evidence that there was, but I'm just saying there's not evidence that there. I don't think that there wasn't. Yeah, I think in principle. Well, in principle, I guess it depends on if this orphan afterglow here, if it's somehow buried beneath this, it may be hard to ever tell. Yeah, so I'm not sure we'll be able to tell. It could be hard. Definitely, if we see another component turn on that's much brighter than this and distinct, that would be evidence for. But if we don't, I don't know if it tells us that there wasn't the off-axis was buried beneath this. So
the gamma of 10 is coming from the X-rays.
it's coming the whole thing. So the gamma of 10 is just coming from. It's coming. Well, yeah, it's coming from the spectral slope and from the timing and other things. Yeah, it's 3 to 10, maybe 2 to 10, but it's not an ultra-relativistic core, and it's not mildly relativistic material. Okay, I don't want to say too much about that, since I want to mainly talk about the kilonova mission, which is what I've worked the most on. So this was an idea before this event, because I didn't think we would be lucky enough to be seeing it on axis and at 40 megaparsecs. The gamma rays, the radio X-rays, it would have been very difficult to detect any of these things if this thing had happened at 100 megaparsecs. So for a long time, I've been focused on the kilonova, because this is a more isotropic counterpart that we should detect in principle from any angle. And this is produced by, it's a thermal transient powered by the radioactive decay of heavy elements which are created in the merger ejecta. And the basic point is that there are several sources of neutron-rich material which are ejected during the merger. You saw the movie. There's this tidally ejected material. This is what most people think of when they think of the merger ejecta. This material tends to come out very promptly in the equatorial plane. It doesn't have much of an opportunity to be shocked or irradiated by neutrinos or anything. So it tends to retain the very neutron-rich composition of the neutron star itself. So typically neutron to proton ratio of 10 or so. Very neutron-rich material, but there's not much of it. There's also material produced as the two neutron stars collide. This material is shock heated and is strongly irradiated by neutrinos in the polar direction. And neutrinos, particularly electron neutrinos, can turn neutrons back into protons. So this material tends to be not quite as neutron-rich, and it depends on exactly how you do the neutrino transport what you get. But both of these come out. I call them dynamical ejecta because they come out very quickly during the merger itself. The largest anyone has ever seen in a simulation is about 10 to the minus 2 solar masses in a simulation with GR. or some approximation of GR. This material comes out very quickly, and it tends to be quite high in velocity. But there's a second source of ejecta from these systems, which I think is actually the dominant one, and I think it dominated this one as well. And these are outflows from the accretion disk, the same one that powered the gamma ray burst. The disk is typically 1/10 of a solar mass if, say, 30 or 40% of the disk is blown out in a wind as opposed to being accreted, which I'll show you why that's the right number in a second. Then this can be a more important source of ejecta than this material. However, this material turns out on a longer time scale, more commensurate with the viscous time of the accretion disk, and it tends to have a lower average velocity because the physics driving the wind is a bit different. Well, anyways, it's not related to the escape speed. It's related to some nuclear physics. And also, this material from the disk can be more strongly irradiated by neutrinos because the neutrinos can come either from the disk itself or from the neutron star before it collapses into a black hole. So I'll come back to that in a second. So what postdoc in my group, Daniel Siegel, did were some of the first 3D MHD simulations of these toruses where we followed all of the relevant weak interactions in the disk, so the things that might change the electron fraction of the disk. And our basic goal was not to try to calculate a jet, which is really hard to do, but just to figure out how much mass is accreted onto the black hole, how much is unbound in winds, and what the composition of that material was. And these disks are interesting because the midplane of the disk can become hot and become cooled by neutrinos. I'll just show you the movie of the density. Oops. The midplane of the disk can be hot and cooled by neutrinos, but you get this, the upper layers cannot cool, so they become this very puffy ADAF type flow. And it turns out that only a fairly small, only a modest fraction actually accretes onto the black hole. What happens is the MRI produces turbulence, which goes up and dissipates its energy into the hot corona. The disk itself is composed of free neutrons and protons, but as in the upper layers of the atmosphere, those recombine into alpha particles, which gives the wind a boost of energy and tends to sort of push it over the edge towards evaporation. And what we find is after the end of the simulation, 400 milliseconds, we find that about 20% of the torus mass has been ejected. If we extrapolate our simulation to infinity, we estimate that about 40% of the torus will be unbound. And this is starting with initial conditions motivated by a merger. So there's a lot of fascinating physics that go into what sets the composition of the disk and related to the fact that these weak interactions tend to regulate the electron fraction to be quite low in the midplane. So if you form a black hole quickly, these disks tend to be quite neutron rich. If you have a longer-lived neutron star, they won't be as much. And with Rodrigo Fernandez, we've studied with alpha viscosity simulations, also the case of a long-lived neutron star, but I'm not going to talk a whole huge about those. But yeah, this is MHD. This is 3D GRMHD, yeah. We spent a lot of time. This was a 5 million CPU hour simulation to try to resolve the MRI. Starting off, and nicely, because his merger produces a fairly magnetized torus, you can actually conceivably resolve it even with the initial magnetic field. Okay, so you start off with your simulation. You have a bunch of test particles in your disk, and then some fraction are accreted, some fraction are blown out. For each one, you have the thermodynamic conditions, so you can follow the nucleosynthesis as this matter expands into the vacuum. So what happens with the R process is quite simple. All of your protons very quickly get together with some of your neutrons as the matter is expanding through normal thermonuclear reactions to form these heavy seed nuclei. But then you have so many neutrons left over, because there's a Coulomb barrier that prevents you from building up too many heavy nuclei through standard thermonuclear reactions, that these nuclei are bombarded and capture neutrons, forming these very heavy, neutron-rich nuclei at a rate much faster than those nuclei can beta decay back to stability. And so this is how you create the heaviest elements. So this is neutron number, proton number. This is the abundances here shown in color. This is the stable valley here. We're following a single fluid element as it expands, so temperature and density are dropping as a function of time. And what happens is you quickly form these C nuclei in NSE. They capture neutrons, they move this way, they undergo beta decays, neutron capture beta decays, and that's how they form these heavy elements. And then once you run out of neutrons, they'll all decay back to stable elements. So at the top, you're seeing a running total of the abundances versus atomic mass number. So we're expanding, we're capturing neutrons, we're going up here at a tenth of a second in. Right about now or so, we run out of neutrons, and then all these elements slowly decay back to the stable value over minutes, hours, days, years, billions of years. I mean, at least if you start off with a sufficiently neutron-rich ejecta, like electron fraction of 0.1 or so, neutron-proton ratio 10, you can form the two R process abundance peaks, the second and the third peak. This is, of course, one where there's a lot of xenon and silver on this peak, platinum and gold, and you can also produce the transuranic elements, which are impossible to produce with the S process, like uranium and thorium. Now, I don't want to say in detail. You can do these simulations, and you have your nice simulation. You can create a very detailed abundance pattern. You can compare it to, say, the solar system or the abundance pattern on your favorite metal poor star. But you don't get perfect agreement, and that's pretty obvious why. Even if we did a perfect simulation, most of the properties of the nuclei over here are not measured experimentally in the laboratory yet. So we have theoretical mass model, theoretical model for neutron capture, beta decay rates, et cetera. And that all influences the details of what you get in the end. Now, a lot of these will be measured, at least in this part, by the facility being built in Michigan State over the next decade. But right now, there are major uncertainties. So you shouldn't trust details of whether things agree. But the point is, you have enough neutrons, you can capture your way up to the heaviest elements, and that's all we can really say at this point.
Beta decay rates understood to order of magnitude?
Yeah. These things are, I think these are sort of understood to order of magnitude. And statistically, a lot of things will fall out of this that are more robust than individual abundances. So if you ask me what is the what is the abundance of gold, whatever, some isotope of gold, I wouldn't be able to tell you with much accuracy. But things like the radioactive decay, which I'll talk about now, are more robust because they're based on a statistical ensemble. Yeah. So the important point for the R process is this material is radioactive. Someone suggested we should call these radioactive nova or radioactive waste nova or something, because that's basically what it is. You're just generating radioactive waste and throwing it into space. So this is the radioactive power per gram per second versus time. The R process itself takes about a second, and then you start decaying. If you just had a single decaying isotope like nickel-56, it would have a constant radioactive heating followed by a half-life. But here you have hundreds of decaying isotopes. So one with a half-life of a minute decays to one with a half-life of an hour, to one with a half-life of a day, et cetera. And when you add them together, you get a power law radioactive heating rate. Now, if you want to power a thermal transient, you have to not just produce radioactive power, which comes out in the form of beta decays, products, alpha decay, and gamma rays. You have to be able to have the plasma absorb that energy and thermalize it. So a second part of this is checking that the charged particles can share their energy with the plasma through Coulomb scattering. The gamma rays can be absorbed. But this is what there's a lot of work. Jennifer Barnes has been doing a lot of work on this recently. And it becomes more tenuous at late times exactly how much of this radioactive power is being generated. But at least over the first few days, it's pretty efficient at thermalizing the decay energy. And it decays roughly as t to the minus 1.3. And it turns out that this is actually roughly the decay you find for terrestrial radioactive waste. So this is my plot where I push my own work here. And just say that when we were first doing this, so this idea of radioactive power transients was around for Lee and Paczynski in '98. And basically nobody worked on it for a decade. I got interested in this because I was at Berkeley, and the observers were not detecting things as bright as Lee and Paczynski said that they should be. And then I went back through and realized that they just had parametrized the radioactive heating. It's just a free parameter, and it could be anything you want here. So I got in touch with some nuclear physicists, and this is their first calculation of what this radioactive heating was. We put it into a radiative transfer, a 1D radiative transfer calculation to just follow the diffusion of the thermal energy. And what we found is, it should be a few 10 to the 41 ergs per second on a time scale a little less than a day. This was 1,000 times brighter than classical nova, so we called it kilonova. And this was just the standard thing. So after this event, various groups measured the light curve, measured the spectra, did bolometric corrections, created a bolometric light curve for this event. So this is my plot where I just overplot our original model on what people said was the bolometric light curve for this data, for this event. And Maria I was working with the Dickham group. She was working with the Santa Cruz and Carnegie groups. But basically, people are disagreeing about this first data point a bit now because the UV correction is hard to do. But large, it actually fit pretty well. And I should say that there's one place where you could see the model predicts like a bump here late times, and everyone always asks me about that. In these original models, the sin of these original models was we didn't know what to assume for the opacity of the ejecta, so we took it to be iron because we had no idea what it should be. And iron has a bump in the light curve that happens when there's a recombination from the second to the first ionization state. You see this in type 1a supernova. You get a change in ionization state, it produces a change in opacity, you get a bump. We don't see that in the data, but that's not surprising because this is not made of iron, this particular ejecta. And the other thing these original models did not get right was the very strong color evolution. So very early times, this event was very blue, which the original models did predict. But then the spectral peak moved into the near infrared, so you've probably seen these spectra before. But 1.5, 2.5, 3.5, 4.5, 7.5, 9.5 days after the merger, this is covering from the UV to the near infrared. This is going a bit further into near infrared, so there's sort of some replication here. But largely, in early times, it was consistent with a black body-like featureless spectra, quite blue-ish. Featureless, presumably because that material was expanding at a sizable fraction of the speed of light. You're not going to see any lines. But as time goes on, you see the spectral peak is moving further into the red, and they start to see these absorption, sort of broad absorption-like features, which are probably coming from some of the nuclei, or sorry, some of the atoms in the ejecta. I'm not going to go into detail into what those elements actually are because well, I'll come back to that in a second. You can ask me, but we don't have good enough models to tell us, okay, that's an absorption trough from neodymium or something. Although that actually is what it is in the theoretical models. We've modeled neodymium quite well. So anyways, there's some debate as to spectra. Is it just one single, spectral thing, or is there like one blue part that's being replaced by a red part?
Is that double hump there just because you guys have different spectrograph?
Well, this is I don't know. Someone can tell me what this is. This is bad data. Yeah. So this is how we interpreted it originally. Was that we had a blue component and then there was a red component. You could say it was also part of one black body and there was like a big absorption feature. I don't know if there's a unique answer, but yeah, we interpret it as two. But exactly, okay, so the question is what sets the color of these kilonova? And it's actually sensitive to the atomic physics. So you get this fascinating interplay in kilonova between the nuclear physics, which tells you what elements you create, how far up the periodic table you go, and what the opacity and color of the emission would be. So the second R process peak is around here in the periodic table. The third peak is down here. And between them is the lanthanides, which don't fit in the periodic table. They go down here because they have. And the reason, remember, the periodic table is based on the valence structure of the electrons. So iron, so I should just say, the opacity in these ejecta, like in a 1A supernova, is not some kind of continual opacity. It's a forest of lines, of UV and optical and even infrared lines. And they're Doppler broadened by the expanding material, which is why they form a sort of pseudo-continuum. Normal 1As, the opacity is dominated by iron, and that's because iron is a half-filled D-shell valence structure. The electrons have many ways to move around in the valence shell of iron and produce many lines. But these lanthanide elements are even more complicated. In a combinatorial way, a half-filled F-shell valence structure is much more complex. There are many more ways to move the electrons around. There are many more lines. And the number of lines, many more levels in the atom, and the number of lines goes as number of levels squared. So there are many more transitions, and in fact, as a result, the UV and optical opacity, if you have just a small fraction of the ejecta contains these lanthanide nuclei, you're going to have a much, much higher UV optical opacity than if you just have an iron nucleus or any other light R process element. So the upshot is if you just have light R process elements, you have atoms with mostly simple atomic structure. But if you also produce up to the third R process peak, you have to also produce these lanthanides and maybe even actinides, and those are going to have a more complex atomic structure. So the idea before this event was we might have different types of kilonova depending on the composition of the material. So if you have just the light R process or iron, which was our original models, you would get something that peaks at about a day and is quite blue. On the other hand, as was pointed out by Dan Kaysen and Masayome Tanaka and Kento Okazaka and Jenny Barnes, if you also have these lanthanides in the ejecta, then the UV optical opacity is enormous, like 100 times higher, and the ejecta has to expand further, and the flux has to leak out in the near infrared. And because it has to expand further, the light curve will last a bit longer through Arnett's law, about a week, and will be significantly redder. But the connection I want to make to you is whether we get a blue fast-evolving kilonova or a red or both depends on the R process itself. If we eject material which is deficient in neutrons, if we eject very neutron-rich material, as I showed you, we can produce all of the heavy elements, including the lanthanides. But if we just eject light, if we just eject material that doesn't have as many neutrons, we're only going to produce, say up to here, and we're going to have this blue evolving emission. So exactly what we see depends on the composition of the material. And in fact, it was also appreciated that we might actually see both from the same event because of a geometric fact. So if we're observing the event up here, a lot of the neutron deficient ejecta, the lanthanide free ejecta, will be coming out in the polar direction. One example is when the neutron stars slam together, there's this shock heated material which goes in that direction. An example, whereas the redder material tends to come out either more spherically or in the equatorial plane. For instance, the tidal material is very neutron rich. It should produce the red emission. And then ultimately, the thing collapses to a black hole, and we might get some kind of wind from the accretion disk. And that could produce, in principle, either the blue or the red emission, depending on how long the remnant survives. So the idea was with this paper with Rodriguez, we could see both. We could see this early blue emission followed by something in the red if we could see both of these components. And this was our theoretical prejudice going into this event. In fact, when they discovered this, I said, OK, now you're looking in the infrared, right, because it's going to become red. And so after this event, we tried modeling the photometry with this kind of two-component model where we have a blue low opacity component and a red high opacity component. And we actually were able to get a decent fit, quite a decent fit to the data, whereas if we just took a single component, we weren't able to get as good of a fit. So this is just showing you the bluer bands, of course, fade very quickly. The redder bands, the near infrared was actually persistent for over a week. And if we do this modeling, what we infer is that the blue, the light R process component, has a few hundredths of a solar mass expanding quite quickly, 0.26 C, whereas the red component has about 3 times as much, but it's expanding closer to 1/10 the speed of light. And they're,
Are the two components being treated sort of like
yeah, they're being treated as individually spherical, and it works out as long if the red was blocking the blue moving faster, then that would be a problem. But we are modeling, because then it would be basically the blue ejecta is so the blue ejecta is transparent to the red light, but the red ejecta would be opaque to the blue light. So as long as your blue stuff is moving faster, then it's sort of a self-consistent picture. But yes, this is all within 2 spherical cow picture. This was using a toy model that I developed for a review article about a month before this event happened that I had not anticipated. So many groups would take over. So there's definitely room for these things to wiggle around. There's definitely room for different geometries. Norm has worked on different sources that could provide additional thermal energy to the ejecta at early times that might masquerade as radioactivity. So there's a lot of work on this. But I was struck by that this actually worked pretty well. So what I just want to say is that, I think we have pretty good evidence that we found a site for the R process, maybe the site. And this is a long-standing mystery going back to Burbidge, Hoyle, Fowler, and Al Cameron in the 1950s. they identified all these nuclear processes that happen in nature, and the one process, the R process, for which we haven't unambiguously seen the astrophysical site until now was the R process. So the very simple back of the envelope thing you can do is say, okay, well, what is, if you look at the Milky Way prior to the sun forming, what rate of R process production would you need to produce the heavy elements per year on average? It's roughly this number. From LIGO, thanks to one detection, we have a volumetric rate of mergers, which you can translate into a per Milky Way rate, or a Milky Way rate per year. And so you can ask the question, how much R process would each merger have to produce in order to produce what we need to pollute the sun with its requisite R process material? And that number is between a few thousandth and a few hundredths of a solar mass. And if you believe our modeling, you know, this event produced a few hundredths, maybe even 5 × 10⁻². And so in principle, we have enough. Even if LIGO tells us the rate is on the low end of their estimates, this simple estimate suggests, okay, we have enough to produce most of the R process in the universe. Now, of course, exactly where these things happen in galaxies, how well it's incorporated into the stars, you know, there's a lot of work left to do. And if you translate, though, if you do assume that the solar abundance pattern was produced in this event, and all we really have evidence for is that the lanthanides were produced. We don't have evidence that the heavier elements were produced. Then you get sort of absurd amount of gold, platinum, uranium being produced in this single event. This is what you give to people that are writing popular articles on this. But like, you know, 50 Earth masses of platinum or something ridiculous. So anyways, but let me talk a little bit about the different sources of the ejecta. So what produced this red kilonova? Well, this much material is too large. It's larger than anyone has ever seen from the dynamical ejecta of a merger. But it very naturally fits our predictions for what should come out from the accretion disk. If it has a tenth of a solar mass, ejects 40%, works out nicely. This is the velocity distribution of the ejecta from our simulations. It peaks at about 0.1 c, and we think it's closely related to this fact that the disk is unbinding itself by recombining. And if you take free neutrons and protons and combine into alpha particles, you release 7 MeV per nucleon. Convert that into adiabatic expansion, and you get a velocity of about 0.1 c. So that actually fits pretty nicely if I just say there was a disk outflow from this system.
So it's thermally driven.
The MRI generates an extended corona, and then this recombination pushes it over the edge. Yeah. Okay. Well, but I think the big question for me is then, what is this blue ejecta source, this high velocity ejecta source? It matches, the velocity of it matches well what people find when the two neutron stars collide. There's an ejecta cloud. It goes in that direction. It has about this speed. That seems to make sense. The quantity is a bit disturbingly high. If you look at equal mass merger simulations by Bausfein, in which there's very little tidal material since they're equal mass, most of the ejecta comes from the collision. They made this interesting plot where they show that ejecta quantity versus the radius of a neutron star. And they find that the only way you get up to this large amount is if you have a very small neutron star radius. And the physical reason is if you have smaller neutron star radii for the same mass, then they basically collide at a higher velocity because they have more time to fall in almost directly upon each other. I don't know if I trust these simulations in detail. I'm sure there's going to be a lot more work on this. But it's suggestive, if true, of a small mass. I've been recently thinking maybe this blue ejecta doesn't come from the dynamical event at all. Maybe it comes from this hypermassive neutron star prior to collapsing into a black hole. If you just have the neutrino-driven wind from this object alone, it isn't going to produce very much mass. Or high velocity, but if you say that this object has a strong magnetic field, similar to magnetars, and it's also rotating necessarily very rapidly, what we showed, this is actually some work I did a long time ago, calculating the properties of these winds with Todd Thompson and Elliott Quadrant, and what we found is that if the thing survived for a tenth of a second or so, depending on the parameters, you can get enough material coming out from this magnetized wind. It's a lot more analogous to a stellar wind at this phase. You have neutrinos which are driving mass off the surface, and then it's being accelerated by the magnetic field. But you need an ordered field, which is about 10 to the 14 Gauss, actually. Okay, I want to finish up quickly. So I don't know. I don't know what the source of the blue eject is. Maybe a jet going through the material accelerated it to high velocities. But that doesn't explain the large quantity. The cocoon models have been discussed by many people, but to me it doesn't explain. Maybe the ejecta mass isn't needed as much if it's heated by something else like Norm studied. So, anyway, so I think people have to start to think about what this, especially if we think that some of this 1.7 seconds delay is related to the lifetime of this object. Okay, I want to say a little bit about what the implications are for the equation of state. Since you have Katerina here, you've probably heard about the upper limits that LIGO was able to place on the tidal deformability of neutron stars. Basically, the neutron stars come in, they start to exert tidal forces on each other, which takes some gravitational wave phase away, which they didn't observe, so they're able to put an upper limit on the tidal deformability, which for realistic equations of state translates into an upper limit on the neutron star radius of about 13.5 kilometers, give or take. I'm not going to talk too much about this. I simply want to say you could also look at a constraint you could place on the maximum mass of neutron stars based on the outcome of this event. So there are 4 possible outcomes. The 2 objects can merge. You can immediately collapse into a black hole. You can live forever. Or you can go through these intermediate phases of a differentially rotating hypermassive neutron star, which is supported by differential rotation, or a supermassive one, which is supported by solid body rotation, even once the differential rotation is removed. And these thresholds for these different outcomes depend on the maximum mass of a non-rotating neutron star for most equations of state. So if you're above 30 to 60% of the maximum mass, you should promptly collapse. If you're below 20% the total mass of the binary, you should form a supermassive neutron star. For this event, we measure the total, LIGO measures the total mass, and then we can infer from the electromagnetic emission the outcome. So we don't think there was a prompt collapse. We see too much ejecta. I think it becomes even less plausible if we didn't have a hypermassive neutron star phase. This threshold depends on the radius of a neutron star. So if you massage this and push it down here, you could actually put a lower limit on the radius of a neutron star, about 10.7. If we had formed a stable supermassive neutron star, it would be very rapidly spinning, potentially very highly magnetized because of all of the shear energy liberated during this, and maybe, talking to Chris earlier, maybe these things have magnetar interiors. It seems likely to be this thing would eventually spin down through magnetic dipole radiation and share a small fraction of that prodigious rotational energy with the environment. If you add together the kinetic energy of the kilonova and the GRB from this event, they add up to at most 10 to the 51 ergs, or few. This thing should have injected at least 10 to the 52 or more into the environment, even if you allow some to go away to gravitational waves. So I think that, I can't say for sure that we can prove a black hole form, but energetically it seems very unlikely. And my student Ben went through this more formally, what this implies. You basically assume a supermassive neutron star formed and how much energy that would be required to be liberated. As I mentioned, we have an upper limit on that from the GRB, and then from that he was able to put an upper limit of 2.17 solar masses, basically demanding that a supermassive neutron star not form. So anyways, the upshot is you start off with this broad parameter space, and from the single event, if you believe everyone, and I'm not saying you should, you could actually start to cut into these models. So lack of tidal detection, tidal deformability pushes you that way. Lack of a prompt collapse pushes you that way. Lack of a supermassive neutron star pushes you that way. So it'll be interesting to see if we get more events if we paint a consistent picture with the outcomes. Very quickly, the future. So LIGO Virgo coming online at 03 this fall. We don't know how many neutron star mergers they will detect. If we get unlucky, it could be 0. If we get lucky, it could be 10. That's kind of the range. But once we reach design sensitivity, even under the most pessimistic scenarios, hopefully if LIGO is able to reach design sensitivity where it can see neutron star mergers to an average range of 200 megaparsecs, we should see these at least once per month, say, or every few months. And so the question is, how do we test these scenarios? Well, we really need to make predictions for how this kilonova and other signatures should depend on the viewing angle and on the properties of the ingoing binary. So one possibility is we could have a viewing angle effect. If the blue emission is produced predominantly in the polar direction, and we produce this tidal material in the equatorial plane, For viewers that are closer to viewing this in the equatorial plane, it's possible that the blue emission could be blocked if it's expanding slower than the red material. So we can look for this effect. We want to find a binary that has basically identical parameters but is viewed edge on and see how it looks. Generally speaking, the reason we get the blue kilonova is that, so if you just take neutron star material and inject it into space, you would only produce these heavy elements and you would only have a red kilonova. So the fact that we see this blue kilonova tells us that some material was irradiated by neutrinos or shock heated. And generally the quantity of that material is expected to go up the longer the neutron star remnant survives. And the longer the neutron star remnant survives is going to depend on the mass of the incoming binary. If it's very massive, it should collapse more promptly. So we generally expect that if you have a smaller ingoing binary mass, you should get a longer neutron star lifetime. And the relative strength of the blue kilonova to the red, or at least should increase. So this is something I'm really fascinating to look at, is what is the luminosity of the blue kilonova at 1 day as a function of chirp mass or something. This will be very interesting. Maybe we'll get lucky and have a particularly low mass binary that doesn't want to collapse into a black hole and does something qualitatively different. Maybe we form one of these millisecond magnetars. Maybe it does eject a lot more energy to its environment but doesn't make a GRB. Maybe it looks completely different. So I'm particularly excited about the very low mass binaries that LIGO finds. And speaking to Kip and others here, give us as much information as you can on these sources. Eventually, right now we're going to go after all of them. When they're happening every week, it would be nice to know which are the ones that might do something interesting, particularly interesting. So my conclusion is that from my standpoint, I was surprised that I felt this is a bit arrogant, but I felt it was a well-behaved merger in the sense that the counterparts we saw had either been seen before or were in some sense theoretically predicted. So let me just recount my one possible picture for what happened in this event, which is probably not a unique one. So the two neutron stars merged, they collided, they were fairly small neutron stars, so they produced a fair bit of shock-heated material that expanded in the polar direction. This material was irradiated by neutrinos, couldn't produce the heavy star process elements, but it did produce these lighter raw process elements, which powered the blue kilonova that we saw at about a day. Then the object formed a hypermassive neutron star with an accretion disk. Let's say then it collapsed to a black hole. That black hole produced a jet which broke through the ejecta. Maybe if we had been more fortuitously aligned, we would have seen a on-axis bright gamma ray burst, but we were off-axis, so we saw this dimmer thing. The orphan X-ray radio afterglow that we saw, maybe it wasn't coming from the off-axis core of the jet, but maybe this shock-heated kilonova ejector, or maybe the jet had some structure. Regardless, we're seeing 10 to the 49 ergs in mildly relativistic material. The accretion disk which fed the gamma ray burst jet not only did that, but it also produced a more spherical wind that was fairly rich in neutrons and also produced the heaviest elements. And we saw this as the emission coming out over a time scale of a week. So I didn't have a chance to talk about everything here, but I think it's a very exciting event. We could have seen this blue kilonova to gigaparsec distances. So if you're interested in using these to construct Hubble diagrams, there may be some new things to think about. But regardless, I think very exciting times ahead. Yeah, thanks.
So we're a little over time. We have some time for a couple quick questions.
What's the best guess for the mass of the black hole?
Well, it would be, so the gravitational mass going in is about 2.7 to 2.8. So yeah, something like that. A little bit less of that because there was some lost in neutrinos. And what? How much? Yeah, I'd say it says something like that. 2.6. Yeah, that would be my guess. Yeah. Maybe.
So I'm trying to understand when you have the winds coming out of the disk, those winds are going to collide. So do they collide when the subsonic or supersonic? Do you get a shock?
Yeah, that's a good question. This is a point that I think is lost. I made the point here in a magnetar wind. But any type of engine, like a disk wind that happens over a time scale of a second, it's not going to be regular. So there, I mean, well, we don't know if it's irregular, but you could imagine that there would be, you know, that you'd have a wind with some variability in it, and that will collide at, you know, kind of the velocity of the wind times the duration of the activity. So a lot of people have been focused on adding thermal energy to the ejecta from cocoons and things. I would say just the source of ejecta, if it's temporally extended, is also going to cause shock heating, you know, further out. That could. So yeah, I think that if it's a magnetar wind or if it's an accretion disk wind, there should be internal shocks within that.
So how strong does the dipole have to be in this case to form a magnetosphere and hold up the torus?
Yeah, so in this case, it would have to be quite large. On these time scales, they would have to be 10 to the 15 or higher. I mean, in order, yeah. But it could be higher than this.
So
but
you could get ejection, your initial ejective just from a propeller.
Potentially, yeah. You'd have to. Yeah, you're right. Yeah. I looked at this. It's a little hard, but if you said 10 to the 16, for sure. Yeah. We could go through the numbers. It depends on time. Yeah, it depends on time. You could definitely get some propeller. Yeah, you could get.
You need a heavy torus for the
Yeah.
red torus.
Yeah. You may be able to get some ejection through this. Yeah, I did some calculations recently. But in this particular model, we assume that it basically pushes to the surface, so you create like a split monopole type in the upper quadrant here.
Just saying, in case anyone's got to run, we'll be taking Brian out to dinner tonight. Probably convening around 6 to leave, shortly after 6. Let me know if you're interested. We might have to make a reservation. Let's take one more question before we do this.
So in case where there's a stable material you just survived for a long time, then your argument is that the rotational energy is really high, and that would have been somehow imprinted on the emission. But at what time scales does this rotational energy leave? If this is stably rotating, then I would assume that the time scale is much larger than seconds for the computer rotating.
Well, it depends on what you think the dipole field is. So, you know, the spin down time scale, if the dipole field were 10 to the 16 Gauss, then it would spin down in, you know, a few seconds. but I think what's relevant, you know, here for comparing to the data is if the kilonova had been given extra boost of energy up to a week, we would have seen, you know, that imprinted in our modeling. So if we had accelerated the kilonova ejector from 0.1 C to C by accelerating with this much energy. So what we really need is the way you could hide this is if you made the spin down time scale much longer than a week. But even then, you know, we now have pretty strong constraints from the radio and X-ray on how much mildly relativistic energy you're allowed to inject. And there we're talking about time scales of months. So I would say if you make the dipole field like less than 10 to the 12, maybe 10 to the 11 Gauss, it could still be sitting there spinning and we wouldn't be able to tell. But if it's greater than 10 to the 12 or so, it should have dumped the energy in on a time scale where we would see some
I
observation.
think a general rule is that the ratio of differential rotation in the interior happens faster than the spin down due to the exterior relativistic wind torque.
Well, I guess I'm assuming here that the internal differential rotation was through some process removed very quickly.
Okay.
And then it's in a solid. So we're not ruling out a differential rotating.
You're demanding stability just due to the.
Yeah, exactly. Because differential rotation, I think that's the key. Differential rotation you can remove, you know, and dissipate as heat in neutrinos, and you're never going to see it. But solid body is persistent. It's harder. You have to have a distortion of the object. You have to have gravitational waves, or some other distortion of the object to exceed the
That's
electron.
something that actually isn't fully appreciated. You know, people are doing calorimetry of magnetar nebulae in the galaxy. Right. But it may well be that a lot of magnetic field is due to differential rotation. It's in the last 0.1, 0.2 solar masses of stuff that's accreted.
Right.
Before the neutron star, and then that is mainly internally dissipated.
Right.
Neutrinos. So what actually comes out in the relativistic wind may not be
Right.
anything like
Yeah.
what you would assume for getting a solid body rotator,
Right.
even though the surface layers effectively were quite rapidly rotated.
Right, yeah. So I think in that case where you have a core collapse, the matter is falling in over a longer period of time. Yeah.
But it's an issue, it's a broader issue.
Yeah. So here I'm not. Yeah, I think we're inferring that this thing was in a differential rotating state and it lost that somehow without injecting enormous amount of energy. So it's kind of proof of that. But what you want to put this constraint is you want to rule out this super. I mean, so even once the differential rotation is removed, you want to remove out that it was stable at that point, and that's what we're trying to do. You basically assume, that it was a supermassive neutron star, and ask how much. I guess another way of thinking about it is a black hole is a great place to store energy in angular momentum. Once it's in the black hole, you may not get it out with a very high efficiency. It's a little harder if it's.
There's only so much angular momentum you can squeeze.
Yeah. You can hide it in a black hole. It's a little harder to hide it in a neutron star. Okay.
Let's thank